Hello, this is Graham Neubig, and welcome back to CS 11747, Neural Networks for NLP. This time I'll be talking about an important topic, debugging neural networks for NLP. So in neural networks, debugging is paramount. Models are often complicated and opaque. Everything is a hyperparameter, including your network size, model variations, batch size or training strategy, optimizer, or learning rate. And each of these can have a big effect on your final result. Also, non-convex stochastic optimization has no guarantee of decreasing or converging loss. So the first way we can start debugging our models is understanding the problems we're facing. So a typical situation is that you've implemented a nice model, you've looked at the code, it looks okay, but your accuracy on the test set is bad. So how do you figure out what to do in this situation? Some possible causes could be training time problems, such as lack of model capacity or inability to train the model properly due to poor hyperparameters, or training time bugs. You could also have decoding or test time bugs, such as a disconnect between your test metrics and what decoding, and failure of search algorithms. You could also be overfitting, and we've talked about a lot of methods to combat overfitting in previous classes. And you also could have mismatch between an optimized function and evaluation. So my biggest piece of advice that I think is really important when considering these issues is that you shouldn't try to debug all of them at once. So you shouldn't be looking directly at your test accuracy and try to guess where your problem is, but rather take a systematic approach that can isolate which of these problems you're actually encountering. So first, I'd like to debug a little bit of issues at training time. So how do you identify training time problems? One thing that you can do is you can look at the loss function as calculated on the training set. And look at this loss function and see, is the loss function going down? And does it go down basically to 0 if you run training long enough? And if not, does it go down to 0 if you use a very small data set? So if the answer to all of these is no, then you probably have a training time problem, which could be a result of several different issues. So the first one could be that your model is too weak. If your model doesn't have capacity to fit the data, then of course it won't be able to learn properly to do well on the task that you're interested in. So one thing for sure to know about is that larger models tend to perform better, especially when pre-trained. And this is even including on test time accuracy. So this figure is from a paper that measured 5 different sizes of models, and you can see that from small, base, large, 3 billion, and 11 billion, the accuracy, even on the held out set, tends to go up as you increase. In addition, larger models can learn with fewer steps. So this is a figure from a very nice paper examining how language models learn. And what you can see here is basically the test loss. And training loss, I imagine, is also similar, although it will show slightly different trends. But what we can see is essentially the smaller models take longer to learn, and they don't converge to as good results, where the larger models actually start learning faster and eventually outperform the smaller models. So the thing on the left here is the number of tokens processed overall. Of course, larger models take more time to compute overall, but once you consider the fact that larger models tend to learn in fewer steps over the data you do have, you can see that actually they're pretty competitive with respect to training time, even with smaller models after a certain point. Another issue you could be facing is trouble with optimization. So if increasing model size doesn't help, you may have an optimization problem. So some examples of this can include that you are using a bad optimizer. So very often in neural networks models, recently we use Atom as an optimizer. So if you're using something else like SGD, you may have issues optimizing. And even Atom itself is not sufficient, and you might need a special learning rate or something like this if you're using transformer models, for example. You could have a bad learning rate. So if you have a good optimizer, you still may need to adjust the learning rate or even have a special learning rate schedule. You could also have bad initialization. So if you've implemented models from scratch by yourself, you need to be very careful about how the parameters are initialized. And you could also have a bad mini batching strategy. So if you're mini batching together shorter sentences and longer sentences, this can also affect your results. So as a reminder, for optimizers, we have things like SGD, SGD with momentum, Attigrad, Atom, and many others. All of these were described in a previous class, so I'll skip the details here. But essentially, you need to be careful about which optimizer you're using. And one good way to do this is to start by mimicking previous papers and using the optimizer that they opted to use. And as I said before, if you don't have a previous paper to reference, Atom is usually a pretty good bet. Another thing that I didn't write on the slide here is that when training transformer models, which are very prevalent, of course, in NLP nowadays, it's common to use Atom with a special learning rate schedule where you gradually upweight the learning rate at the beginning of training and then let it drop off as you get later into training. So if you want to train these models, make sure you use a schedule, which should be implemented in most toolkits that you have available to you. So another thing is learning rate. So I already mentioned this before. And learning rate is a low, important parameter. If it's too low, you may not learn or learn very slowly. And if it's too high, you could learn for a while and then fluctuate and diverge. So as I said, the common strategy is to start from an initial learning rate, then gradually decrease. And another thing that I should point out is depending on the optimizer you're using, the default learning rate could be different. So for SGD, the default can be 0.1. For Atom, the default would be 0.01. So again, I'll reiterate that you should look at the defaults and also look at previous work to see what they used here. So don't just ignore this detail. Another thing is initialization. So as I commented previously, I believe, neural nets are sensitive to initialization because this results in different size gradients. And standard initialization methods include Gaussian initialization, where you initialize with a zero mean Gaussian distribution. Uniform range initialization, where you simply initialize uniformly within a range. And other initialization methods that essentially initialize in a uniform manner, but they specify the range according to the size of the net. And this was also included in homework number 1, so I think people are familiar with at least Clairaut initialization. Another thing is that you should be careful when you're using multi-layer models. And in particular, if you make more layers or make a bigger model, that can be very beneficial, as I stated before. But optimization also can get harder because extra layers may help your training, but they can also hurt if you're not careful due to vanishing gradients. So just like in LSTM, it had vanishing gradients, or is in a method to combat vanishing gradients over different time steps, you might need methods to do this over different levels of a multi-layer model. So some solutions include residual connections, where essentially you have intermediate nonlinear transformations and affine transforms, but then you add the input back into the output. So instead of just taking X and transforming it, you take X and transform it, but then you also add the original input. There's another method called highway networks, which is very similar, but instead of just adding the output, you have a gating function that says whether you want to add the output or maintain the input. So residual connections also are featured in transformer models. So if you're using a transformer model, this is kind of already included in your model, even if you are just using the quote unquote transformer layer implemented by a toolkit or something like this. Okay, so these were some examples for how you can check your model to see if you're encountering any training time problems. The next thing I'd like to talk about is debugging at test time, and in particular, debugging models for structured prediction like sequence models. So one issue is that you can have disconnects between what you're doing at training time and what you're doing at test time. And one reason why you can have disconnects could be due to bugs in your code, which results from having the loss calculation that you use at training time and the prediction function that you use at test time being implemented in different places. And this is especially true for structured prediction models such as encoder-decoders. And in fact, we have shown a code example of the encoder-decoders that have different calc loss and generate functions, where the calc loss function is the loss function and the generate function is the one that actually generates the output. So like all of software engineering, duplicated code can be a source of bugs, so this is something you want to check carefully. Also, usually loss calculation is mini-batched, whereas often generation code is not. So because of this, you might also have differences between mini-batched code and non-mini-batched code. So speaking of which, how do we debug mini-batching? So when you have a mini-batched loss calculation, there's a way that you can measure whether you have done everything correctly and basically implemented this in an appropriate way. And the way we do this is we take advantage of the fact that essentially when you're calculating over mini batches, you should still be getting the same result as if you calculated each of the elements of the mini batch independently. So the first thing you can do is calculate the loss with a large batch size, for example, 32, and then calculate the loss for each sentence individually and sum them together. And the values should basically be the same. Minus numerical precision errors. So the good thing about this is if you have an error in your batched loss computation, it's very easy to detect by performing this procedure. Also, if you're implementing a new model, you can create a unit test that explicitly tests this. So you create a separate piece of code that you run periodically to check whether this holds for your model. And unit tests, one of the good things about them is they essentially are these little tests that you create and run periodically. So if you ever break your code by adding new changes to it or something like this, this unit test can catch it, and you can go back and recheck the area to make sure that everything is working appropriately. So I'd highly encourage this. Another thing is decoding or debugging structured generation. So your structured generation or decoding code can also be a big source of errors, as I said before, because it might be implemented in a different place in your loss code. However, assuming that you are trying to generate outputs that have high conditional probability, your decoding code should actually get the same score as your loss calculation. And so a way you can test this is call the decoding function to generate an output. So you basically generate an output and keep track of the score that you get during the search procedure that you have implemented. And then you can call the loss function on the generated output. And the score of these two functions should be the same. So, if you're talking about translation, you generate a translation, then you calculate the loss of the generated translation, and that should be the same as the score that you got during search. And this is another thing that you can create a unit test for. So I've talked previously about beam search, which instead of picking one high probability word during search, maintains several paths. This being one example of a beam search that has two different paths included in it. And this is an ubiquitous search procedure that we apply in many of our models. And however, it's a little bit more complicated than a lot of the things that we implement in, loss calculation or something like this. So it's very prone to be a source of errors. So how do we debug search? And essentially, as you make search better, the model score should get better almost all of the time. So one thing that you can do is you can run search with varying beam sizes. So beam search is an approximate search algorithm where if you make your beam larger, the search algorithm should get better. So you run search with varying beam sizes and make sure you get a better overall model score with larger sizes. And we can create a unit test testing this. So a final really powerful tool for debugging any test time errors is to look at your data. And I mean, this should kind of go without saying. If you're building a system that you actually care about, what you finally care about are the outputs generated by the system, so you should be looking at them. But sometimes, when people are starting out with research, they don't necessarily consider the data as carefully as they do the overall numbers that they're getting. So this is just a reminder that you should definitely be looking carefully at your outputs and make sure they kind of match your intuition. So some examples of issues that we can find by doing this, and these actually I've seen this over and over again. The first word of the sentence is dropped every time. So we have like went to the store yesterday, or bought a dog, when it should be like I went to the store yesterday or he bought a dog. And if this is the case, you might just have a off by one error where you're forgetting to output a single output. And you would be getting low scores because of this, but you might not necessarily be able to quickly identify what's going wrong if you don't look at the data itself. Another kind of funny example is one time we had a system that was making University of Nebraska at Kearney's acronym in unknown word because it's UNK, and we only found this by looking at our data very carefully. So one thing that we are going to do now is I'm going to turn this over to Pengfei, the co-lecturer for today, and he's going to be talking a little bit about how we can perform more systematic quantitative analysis of your data that can also help overcome these problems.
Okay, let's get started. So in the previous slides, Graham has mentioned one situation, that is, you have already implemented a nice model. However, the text performance is not that ideal. So we then formulated this problem as a model debugging task. And then we have explored different approaches, which either from the perspective of the training stage or the perspective of the text stage. So then we try to know another common situation, that is, you have already implemented a nice model and the text performance is pretty good. However, you want to know what the potential limitation, what the potential weakness of your system are. So regarding this problem, we usually formulate it as a model diagnostic task. So what's it? The model diagnostic aims to identify the limitations, the weakness, or even the strengths of your model. So why do we need it? One straightforward answer to this question is by performing the model diagnostic, given a system, it could allow us to get a better understanding of what works of the system and what potential next step is. So this is one example. This figure illustrates how the performance of the NER task changed over the past 3 years. So the y-axis represents the F1 scores of the NER task. The x-axis represents the different years. So intuitively, we can observe that during the last 4 years, the performance of on the NLP task has reached a plateau gradually. So this is not the only case. Actually, in many RP tasks, they suffer from the problem. So based on this background, when questions could be naturally raised, that is, how to further improve the performance. So we can understand in this way, if we said the model debugging is would be helpful for us for our assignment 4, whose goal is to achieve a state of the art system, then the model diagnostic would be would become a really useful general methodology for our assignment 4, whose goal is to further improve the state of the art system that we have already achieved in the assignment 3. But how to achieve this goal, how to achieve the system diagnostic, there are three general methodologies we would detail later: the error analysis, diagnostic evaluation, and the interpretable evaluation. So here I have tried to prepare some recommended papers, maybe 3 or 4 master read papers for each method. Feel free to check them. Um, so for the error analysis, one point is it happens at the text stage. And the general goal is to identify the mispredicted text samples and then try to summarize the commonalities of these mispredicted samples. So here is an example. This is a result, an error analysis result on the task of sentiment classification. So we find the classifier of the sentiment classification model will fail when dealing with the following 3 types of samples. the first the first type is sentence with double negation. So for example, I don't think this movie is not interesting. The ground truth answer of this sentence is positive. However, our model mispredicted as a negative. The reasons why the system failed probably because it cannot properly handle the long-term dependency between the words don't and the words not. So maybe one evidence from this error case is, okay, if we want to further improve the system, we probably need to incorporate some neural modules which could handle the long-term dependency. This is the first error pattern. The second error pattern is the samples with subjunctive mode. For example, the movie could have been better. The ground truth label is negative. However, the model couldn't figure it out. The potential reason probably because the system lacks the reasoning ability. So one inspiration from this error pattern is to incorporate some modules with reasoning ability as the future work. So the third error pattern is samples with annotation errors. So which means the our model actually has precisely predicts the samples. However, the ground truth label are wrong, which means the annotation of the text samples are not perfect. So which just inspire us that maybe we should perform some denoising operations or clean the text sample before we use it. So in a word, regarding the uh, error, error analysis method, it is a naive but super useful methodology. So actually, learning to perform error analysis is a really good research habit because many useful or many solid ideas just come from a good error analysis. And at the same time, one interesting thing is when you try to perform the error analysis, you are not correcting the system at the same time, you're also correcting yourself because the error analysis just provide you with an opportunity in which you could play with the data closely and simultaneously you can acquire the domain knowledge of this task. So for example, if you make the error analysis on the sentiment classification task, by examining the different error patterns, finally you would become an expert in the sentiment classification. So there is a potential limitation of the error analysis. Previously, we have summarized 3 types of error patterns uh, by examining the text samples. However, one problem is, what if there is no the second error patterns sample in the text set? I mean, the text set only include the samples with the error pattern 1 and the error pattern 3. So to address this problem, one intuitive solution is just to construct the samples with error pattern 2. So this is exactly the core idea of the second methodology for system diagnostic, that is diagnostic evaluation. And the high-level idea is first to automatically construct a new text samples which could fool your current learning system. And then you re-evaluate your system by using the newly constructed data. So here is one side note, that is when you try to read in the paper relevant to the diagnostic evaluation, most of the time they don't they don't explicitly mention that, okay, this is a diagnostic evaluation paper. Yeah, by contrast, they use different names for their new set of text samples. For example, the stress set, the contrastive set, or the adversarial set. So just keep this in mind. In case later when you have encountered these keywords, just realize that, okay, this is a research about the diagnostic evaluation. There is also one potential limitation of the diagnostic evaluation, that is confirmation bias. So recall that uh, the major step of a diagnostic evaluation is to construct a new text samples. However, how do we know what types of samples we should construct? So usually in the diagnostic evaluation, we try to assume that our model will fail when dealing with a specific samples with some error patterns. We do it beforehand. So how to alleviate the potential confirmation bias? Let's try to know the third methodology of the system diagnostic, that is interpretable evaluation, which could slightly alleviate the confirmation bias, but not completely. So we can understand the definition of interpretable evaluation from its motivation, which is a good evaluation metric can not only rank different systems, but also could highlight the strengths and weakness between them. So, but how to achieve the interpretable evaluation? If using one sentence to summarize it, that is, by partition the performance of the text set into different interpretable groups based on a predefined attribute. So this sentence implicitly suggest 3 major steps of the interpretable evaluation: attribute definition, and the test sample partition, and the performance breakdown. So here is one example using the named entity recognition task. So the goal is to identify the entity New York in the text sentence. So as suggested, the first step is to define the attribute with respect to the New York. And here, there are a bunch of attributes could be defined. And one attribute here is the entity length of the New York. EN represents the entity length. And then based on the attribute value, I mean the value of the entity length, 1, 2, 3, on the larger than 4, we could partition all the text samples into 4 groups. And then we can calculate the fine-grained performance on each bucket, on each category. So finally, we could obtain a performance histogram. Here, there is a side note that is of the attribute, that is different tasks could have different attributes. Some of the attribute could be shared across different tasks. However, some attributes are probably task specific or task dependent, and how to define this task specific attribute depends on your deep understanding of the task. So yeah, there are also some um, typology to define the attributes, like the token level, span level, and the sentence level. Which one should be choose? It also depends on the different forms of the task. So let's see what's the use of the performance histogram. There are two major applicable scenarios. The first one is used for the single system diagnostic. So by using the performance histogram, at least we can easily to know on which bucket the system could do better, on which bucket the system perform worse. So secondly, the performance histogram also could help us to compare two systems. So for example, when you want to compare the differences between the BERT-based system and MO-based systems, you can first calculate the performance histogram of these two models separately, and then use the first one to minus the second one, therefore obtaining a performance gap histogram. That is this one. By examining from the performance gap histogram, it would be very intuitive for us to know, to figure out, okay, when BERT would outperform MO and when MO would surpass the BERT. So in summary, for the interpretable evaluation, there is no need to construct the new samples, and there is no need to think about the potential error type beforehand. But one thing that is really be needed, that is we should predefine the attributes based on our understanding of this task. So here is a detailed comparison between the three methodologies, it's error analysis, diagnostic evaluation, and the interpretable evaluation. One commonality among these three methodology is all of these three methods happen at the test stage, and all three methods require human effort more or less. Specifically for the diagnostic evaluation, it requires an additional test set. So maybe you have already observed that for all three methods, it more or less require human effort. So one question is, can we try to automate the system diagnostic method? So finally, we will share our two existing toolkits for the system diagnostic. We try to introduce two awesome toolkits which could automate the interpretable evaluation, this specific methodology. The first one is the compare MT. The compare MT basically is a diagnostic analysis toolkit specifically designed for the machine translation task. And the general idea is, instead of using a holistic evaluation metric like the blue, it suggests us to break down the performance into different categories by a predefined attribute, like what we have discussed previously. The attribute could be the sentence length or the part of speech text. So here is an example. It illustrates how compare MT is applied to compare the two popular motion translation system, phrase-based motion translation and the neural network-based motion translation. The axis, so in this figure, in this histogram, the x-axis represents the different intervals of the attribute sentence length. The y-axis represents the metric score, the blue score. And from this histogram, we can easily to obtain that, okay, in most of the time, the neural network motion translation system could outperform the phrase-based motion translation system. However, when dealing with the longer sentence, the phrase-based motion translation system could surpass the NMT, neural network-based motion translation system. So the second toolkit is the Explanatory Board. So basically, it is a next generation of the leaderboard, which has two major rules. The first is to track the NLP progress. The second is to help researchers diagnose the NLP system. So the leaderboard is not a new thing, right? You can easily to get the leaderboard either from the paper with code website or the NLP progress website. So here is one example. So for the Explanatory Board, this is the brief description of it. Comparing with the Compare MT toolkit, Explanatory Board could cover more NLP tasks, and comparing with Leaderboard, the Explanatory Board not only include a ranking list of the model on a specific NLP task, it also has been equipped with multiple analysis buttons, which could allow you to get a better understanding of a system, of a model that you have already selected in the table. So for example, if you want to get a performance histogram of a specific model, you just need to select the rule and then click a specific button, then you could get a fine-grained evaluation of the system over different attributes you have already defined. So here is the case. So here's a summary of the Explanatory Board. It could cover more NLP tasks, and it is equipped with more functionalities, which could allow you to make interpretable, interactive, and reliable analysis of any system you have already chosen in the leaderboard. So here is a GitHub of this toolkit. And also, this is still an ongoing project. So feel free to play with it and also leave your comments. Okay, that's all.
Okay, so now back to me. The final thing that I want to talk about is mismatch between optimized functions and evaluation metrics. So the loss function in the evaluation metric, it's very common for us to optimize something like likelihood for training. And the reason for this is simple. Likelihood is a continuous function that is easy to differentiate and backprop through. However, even though likelihood is getting better, accuracy can get worse. And this is because accuracy is the result of doing argmax decoding and comparing the output with the actual outputs that we get or that we expect on our data set. So these are two different functions. Very often they're highly correlated, but they're not exactly correlated. So to give an example of this with classification, loss and accuracy are decorrelated here. So if we look, we can take a look at the training set, loss and accuracy, and the test set, loss and accuracy. And on the test set, we can see that loss goes down very quickly, and then after a few iterations, it starts to get worse and worse and worse and worse. And On the other hand, we see accuracy essentially is getting better and better and better and better as we continue training. So why is this? Basically, the reason why, and this loss is the negative log likelihood of the correct output. And basically, the reason why is because as you train the model more, the model can get more confident about its mistakes. And so it has a few mistakes that it gives a very high probability to the wrong answer. And because of this, the log likelihood of the correct answer actually gets very, very poor log likelihood. However, for accuracy, the model starts to fit these kind of like rarer examples or rarer patterns. And because of this, it needs to have a sufficient amount of training before that happens. So one issue with this, for example, is early stopping, where if we stopped training when the loss was lowest, we'd actually get an accuracy that's maybe a full percentage point worse than if we just let it keep on training for 50 epochs. So how do we manage the difference? The most principled way is to use some sort of technique that more directly optimizes the metric that we want to be optimizing. And specifically with respect to structured prediction, we're going to talk about structured max margin training, minimum risk training, and reinforcement learning as methods to do this. But a much simpler method is early stopping with the evaluation metric. So I alluded to this just before. So instead of stopping where the loss is lowest, we stop where the accuracy is highest. And you can see this could result in a very large difference between which epoch we decide to early stop with. Okay, so I'm going to go into a few final words. And specifically, I'm going to go into a few final words with respect to reproducing previous work. And the previous work, reproducing previous work is an important part of research in any area, including NLP. But reproducing previous work can also be hard because everything is a hyperparameter. And if code is released, this makes our life a lot easier. So you can run the code yourself, or if you want to reproduce it in your own framework, you can look at the previous code and find and reduce the differences one by one. If the code is not released yet, it makes things a lot harder and you'll have to try your best. But one thing I'd highly, highly recommend is to just feel free to go ahead and contact authors about details of their work. And you know, researchers are always happy that other people are using their work. That's the reason why they become researchers most of the time, because they want to build something useful. So usually in my experience, people will respond and try to be helpful with this. Okay, so that is all for today. I would, as a discussion question, I would like people to share their own debugging horror stories and maybe some examples of things that you tried to debug but had a lot of trouble debugging, but then finally figured it out, and how you managed to do that would be particularly useful experience for other people in the class. So thanks a lot, and that's all I have for today.